Hello students, welcome to the course 21SMAC244B Polymer Analysis. And in this chapter we are going to discuss the analysis and testing of polymers. There are various standard techniques used to identify the chemical structure of polymers. As a starting point, the common methods for the functional groups and elemental analysis used in the analytical chemistry are applicable. The spectroscopic techniques, including infrared, Raman, ultraviolet visible, nuclear magnetic resonance, and emission spectroscopies, are regularly used by polymer scientists. In addition, thermal analysis, for example, differential scanning calorimetry, that is DSC, is an important identification technique for polymers. Mass spectrometry and chromatographic techniques, including gas chromatography, HPLC, and TLC, can also be used to separate components and may be used to identify both monomers and additives. There are a number of simple methods that can be used to check types of polymers. This includes solubility tests, melting temperature determinations, density measurements, flame tests, and pyrolysis tests. There are also numerous standard chemical tests that can be used to identify the functional groups present in various polymers. Let us discuss these properties in short. The first property of the polymer is solubility. A check of polymer solubility provides a simple method for distinguishing polymers in the first instance. The solubility can be determined by placing 0.1 gram of the polymer of interest in a test tube with about 5 ml of a particular solvent. As some polymers may take a longer period of time to dissolve, it is advisable to check the sample after standing for several hours. The tube may also require heating to induce solubility. There are polymers which are soluble in particular solvents. So based on their solubility, we can identify which type of polymer is present in the obtained sample. This table shows some properties of the polymer with respect to the solubility in solvent. For example, the polyethylene is soluble in all hydrocarbons. Polypropylene is also soluble in hydrocarbons. PVC is easily soluble in dimethyl formamide, tetrahydrofuran, cyclohexanone, methyl ethyl ketones, etc. If obtained sample is soluble in these solvents, we can assume that the sample may contain PVC. Similarly, there are a number of other solvents are also there which are specific to the polymers especially. The second property is density. We all know that density of a material is the ratio of mass to the volume, and it can be given by the equation rho is equal to m by v. The simplest method for determining the density of a polymer is the use of a flotation procedure. And this flotation procedure involves floating the polymer sample in a liquid of known density. For example, the samples can be immersed in a columns of methanol with a density 0.79 grams per centimeter cube, water with a density of 1 gram per centimeter cube, or saturated aqueous magnesium chloride solution, or we can use saturated aqueous zinc chloride solution. The behavior of the samples is then observed, and the observations are done with respect to whether the sample remains on the liquid surface, it floats within the liquid, or it sinks. The specific behavior determines whether the polymer has a lower or higher density than the liquid in which it is immersed. And based on this, we can identify which type of polymer is present in the sample. This table shows the densities of various common polymers. For example, the silicon rubber has the density of 0.80. The polyethylene tetraphthalate has the density in between 1.38 to 1.41. The amino resins has density 1.47 to 1.52, etc. The heating a polymer sample can provide a number of preliminary approaches to the analysis. The flame tests can be used to differentiate polymers as the flame produced by a burning polymer shows characteristic differences dependent on the structure of the material. In order to test the behavior of a polymer in a flame, a small piece of material can be held with a spatula or the pair of tweezers in the low flame of a Bunsen burner. The appearance of the flame and the production of any odor should be noted. For example, when polyethylene is heated in a flame, it produces yellow flame with a blue base, and the smell or the odor of the polyethylene is like the burning candle. Similarly, the polyvinyl chloride, when heated, it produces again a yellow flame with a green base, but the odor is like of acrid. The nylons, when they are heated in a flame, they produces yellow flame with a blue smoke, and they are odorless. Similarly, there are number of polymers are there. So based on the color which is produced in the flame and from the odor, we can identify which type of polymer can be present in the sample. The degradation behavior of a polymers can be studied by using pyrolysis tests. Thermal degradation produces low molecular weight fragments that are often flammable or have a characteristic odor. A polymer sample can be heated without direct contact with the flame by placing a small piece of the material in a pyrolysis tube and holding the tube with tongs in a Bunsen flame. At the open end of the tube, a piece of moist litmus or pH paper is held in order to determine the nature of the fumes produced. The polymer can be distinguished as acidic, basic, or neutral. This table shows when the pyrolysis is carried out for polystyrene resins, it shows the pH in between 0.5 to 4. Similarly, silicon shows the pH 5 to 5.5, and nylon shows the pH in between 8 to 9.5. So based on these, we can identify the nature of the polymer, whether they are acidic, neutral, or basic in nature. For thermoplastics, the melting temperature may be used to identify the polymer. The melting behavior can be observed by using a standard melting point tube or with a hot stage. The latter device provides a temperature gradient which is created by resistance heaters along a metal bar. A small piece of a sample are placed directly at different points on the metal bar, and the temperature at the border between solid and the molten material is determined directly from the scale on the hot stage. This table shows melting temperatures of some common polymers, like natural rubbers will melt at a temperature of 20 degrees Celsius, polyvinyl alcohols melt at 35 to 85 degrees Celsius, nylon 6 will melt at 215 to 225 degrees Celsius, etc. The infrared spectroscopy is a very popular method for the characterizing polymers. This technique is based on the vibrations of the atoms of a molecule. An infrared spectrum is obtained by passing infrared radiation through a sample and determining which fraction of the incident radiation is absorbed at a particular energy. The infrared spectrum can be divided into three regions, namely far infrared, mid infrared, and near infrared. And most infrared applications employ the mid infrared region, although the near and far infrared regions can also provide specific information about the materials. The near infrared region consists largely of overtones or combination bands of a fundamental modes appearing in the mid infrared region. The far infrared region can provide information regarding lattice vibrations. Spectrum interpretation is simplified by the fact that the bands that appear can be assigned to a particular part of the molecule, thus producing what are known as group frequencies. And the mid-infrared spectrum may be divided into the four regions: XH stretching region, triple bond region, double bond region, and fingerprint region. The information provided by these regions can be summarized in a correlation table, and the correlation, this figure shows the frequencies of different functional groups present in the molecule. From this correlation table, we can assign and identify the type of functional groups present in the polymer backbone or in the polymer subsequents. The next type of technique which can be used to identify the polymer is Raman spectroscopy, and Raman and infrared spectroscopies are based on the same physical process. However, the interaction between the stimulating electromagnetic radiation and the samples differ in these methods. Another way in which electromagnetic radiation may interact with a molecule is being scattered. The scattering with a change of frequency is called Raman scattering, and the change of frequency is equal to the frequency of one of the normal modes of vibrations of the molecule. As with infrared spectroscopy, correlation tables can be used to assign Raman modes to a particular functional groups. And this is a correlation table for Raman spectroscopy to assign the frequencies to different functional groups present in the polymer. Raman spectroscopy has the advantage that a variety of sample types can be examined with a minimal preparations. Solid polymers in the form of powders, films, or fibers can be studied, and there is a range of appropriate solid cells commercially available for this purpose. Liquids can also be examined by using silvered glass cells, and thus polymer solutions and melts can be readily investigated by using this technique. Similarly, nuclear magnetic resonance spectroscopy is a very effective tool for the study of polymer structure both in solution and in the solid state. NMR utilizes the magnetic moment possessed by nuclei whose atomic number or mass number are not both even. Some of the nuclei include H1, C13, N15, O17, and F19. For the quantitative analysis of the polymers, ultraviolet visible spectroscopy is used. Quantitative analysis in the UV visible spectroscopy can be carried out by using the Beer-Lambert law, which is given by the equation A is equal to epsilon into C into Cl, where A is the absorbance of the solution, epsilon is the molar absorptivity, C is the concentration, and L is the path length of the cell. The molar absorptivity is a proportionality constant and has a constant value for a particular compound at a given wavelength. The term thermal analysis describes a number of techniques which involve measuring a physical property of a material as a function of temperature. There are two such thermal methods which are commonly used. and may be used to compare and evaluate the polymer samples are differential scanning calorimetry and differential thermal analysis. DSC, that is differential scanning calorimetry, is a technique which records the energy necessary to establish a zero temperature difference between the sample and a reference material as a function of time or temperature. In this method, the two specimens are subjected to identical temperature conditions in an environment which is heated or cooled at a controlled rate. In contrast, DTA, that is differential thermal analysis, involves measuring the difference in temperature between the sample and the reference material as a function of time or temperature. The next is the mass spectrometry, and this technique involves the study of ions in the gas phase. Mass spectrometry is a widely used technique for the identification of materials, and characteristic mass spectra for many compounds have been collected in a databases. The identification by this technique relies on the fact that the fragmentation of molecules is reproducible. For example, the mass spectrum of a copolymer allows the average composition to be determined. And this mass spectrometry has proved particularly useful for the identification of polymer additives. Chromatography technique are suitable for polymer analysis. There are a number of chromatographic techniques which can be utilized for the identification of the polymers. These methods involve the separation of sample components. Gas chromatography, high performance liquid chromatography, and thin layer chromatography are all techniques that may be used for identification purposes. The gas chromatography can be used to study the volatile components of the polymers. The sample in a gaseous mobile phase is passed through a column containing the liquid stationary phase. The retention of the sample depends on the degree of interaction with the liquid phase and its volatility. The column is usually heated in the range of 50 to 300 degrees Celsius with a flame ionization detector commonly being employed as the detection system. Standard GC can be used to quantify polymer additives and the monomers. This technique has been widely used to monitor volatiles in a polymer used, for instance, in packaging and in paints. One of the advantages of GC is that it has the ability to combine with other analytical instrumentations. Like the GC can be combined with mass spectrometry and IR spectroscopy to identify the separated components directly. High HPLC, high performance liquid chromatography, is used to identify and quantify the low molecular weight species present in polymers. The technique involves injecting the sample into the solvent stream, and the solvent usually consists of two or more components that may be varied in composition with time. The sample flows through the column packed with silica, and separate bands are then detected by using an ultraviolet or refractive index detectors. There are two separation modes used for polymer analysis, that is normal phase and reverse phase. Normal phase chromatography involves separation carried out by using a polar stationary phase and a non-polar organic mobile phase. While in reverse phase chromatography, the stationary phase is non-polar, with the mobile phase being polar in nature. The third chromatographic technique is thin layer chromatography, which is a very simple chromatographic method which may also be used to identify polymers. In TLC, the stationary phase is coated as a thin layer onto a plate. The polymer solution is applied as a spot on the bottom of the plate, and the latter is then placed in a tank containing the mobile phase. The mobile phase is usually a mixture of solvents. The separation occurs as the solvent is carried up the plate by capillary action. The separated components are usually detected by spraying the plate with a suitable visualizing agent. The TLC can be used to identify and characterize homopolymers, copolymers, and additives. And the last technique which can be used to identify the polymers from the sample is the emission spectroscopy. When the molecules absorb radiation in electronic transitions to form excited states, the molecules may lose the acquired energy via several mechanisms. If the energy loss occurs through the emission of radiation, the process is known as luminescence. The fluorescence is a form of luminescence and it involves emission occurring from the lowest excited single state to the singlet ground state. The fluorescence ceases immediately the exciting radiation is removed, with the lifetime usually being of the order of 10 raised to minus 8 to 10 raised to minus 10 seconds. The orange and green colors of some of the fluorescent dyes in common use are examples of this phenomenon. Such dyes absorbs in the ultraviolet and blue electromagnetic regions and the fluorescence in the visible region. The phosphorescence is another form of luminescence and it involves emission occurring from the lowest excited triplet state to the singlet ground state.